On August 24, 2016, astronomers announced something that changed everything about our future. A planet orbiting Proxima Centauri, the closest star to our Sun, just 4.24 light-years away. For the first time in history, we knew with certainty that our nearest stellar neighbor hosted a world. This was not a distant dream anymore. This was a destination we might actually reach. But before we celebrate finding that nearest world, we must understand what we have learned. Since 1992, humanity has confirmed the existence of over 5,000 planets orbiting distant stars. Each discovery taught us something new about what planets can be and where they can exist. Gas giants orbiting closer to their stars than Mercury orbits our Sun, impossibly hot. Ice giants in the outer reaches of their systems, frozen solid for billions of years. Super-Earths with masses 10 times our planet, crushing gravity that would kill us. Water worlds covered entirely by oceans hundreds of kilometers deep, with no land anywhere. And among all those thousands of worlds, perhaps a dozen might support human life. The question is not whether habitable planets exist. We know they do, scattered across the galaxy. The question is, which ones we could actually reach with technology achievable in our lifetimes. Distance kills more dreams than any hostile planetary condition ever could. A planet perfect in every way becomes worthless if it sits 1,000 light-years away. So let us rank humanity's options not by perfection, but by the brutal physics of accessibility. Starting with the worlds that captured our imagination but will never feel our footsteps. In 2015, NASA announced Kepler 452b with a press conference that made international headlines. They called it Earth's older cousin, a planet orbiting a Sun-like star in the habitable zone. The numbers seemed almost too good to be true for anyone dreaming of a second Earth. Orbital period, 385 days. Nearly identical to our familiar year around the Sun. The star itself, a G-type yellow dwarf, older than our Sun, but remarkably similar in size. Planet radius, 1.6 times Earth. Large enough for substantial gravity, small enough to potentially be rocky. If you closed your eyes and imagined the perfect refuge, Kepler 452b matched that vision. 6 billion years of potential evolution on a world bathed in sunlight almost identical to ours. But there exists one number that destroys every romantic vision we might construct around it. Distance, 1,400 light-years of empty space between us and that potentially perfect world. Light traveling at 300,000 kilometers per second takes 14 centuries to cross that void. Our fastest spacecraft ever built, Voyager 1, would require 26 million years to arrive there. Even theoretical fusion rockets achieving 1% light speed would need 140,000 years of travel. That is longer than modern humans have existed as a species anywhere on Earth. No ship we can imagine survives that long. No crew preserves purpose across that time. Kepler 452b represents everything we hope to find and everything we cannot reach simultaneously. The universe's cruelest lesson is that it places its best gifts just beyond our grasp. Then we discovered Kepler 62f through the same telescope that found its famous cousin. Located 1,200 light-years away, similarly unreachable, but fascinating for different reasons entirely. The planet measures 1.4 times Earth's radius, orbiting its star every 267 days comfortably. Computer models analyzing its mass and distance suggest something extraordinary about its surface. A global ocean covering the entire planet, potentially hundreds of kilometers deep, without interruption. No continents rising above the waves, no islands, no solid ground anywhere beneath endless water. At extreme depths, pressure transforms water into exotic ice phases that remain solid despite warmth. Ice 7 forms at 30,000 times atmospheric pressure, denser than steel, harder than granite. The ocean floor would not be rock, but rather this compressed ice extending downward forever. Any human settlement would float perpetually, artificial platforms the only ground that exists. Mining becomes impossible. Agriculture as we know it cannot exist. Metals remain locked away. You could survive there with advanced technology capable of extracting resources from seawater. But if that technology fails, if systems break down, no raw materials exist to rebuild anything. Kepler 62f teaches us that habitable and colonizable are two fundamentally different concepts. A planet might support life without supporting the kind of technological civilization we require. Gliese 667c orbits much closer to us, just 23.6 light-years distant in cosmic terms. The planet completes an orbit every 28 days around its red dwarf star in a tight circle. That proximity creates tidal locking, the same face always pointing toward the star eternally. One hemisphere bakes under constant starlight, while the other freezes in perpetual darkness. Temperature differentials drive winds of incomprehensible violence between these two extremes constantly. Habitable zones would exist only in the narrow twilight band circling the terminator line. But gravity presents an even more fundamental challenge than the atmospheric violence does. At 3.8 Earth masses, surface gravity would be nearly double what our bodies evolved for. Standing there means weighing twice your Earth weight, every movement requiring greater effort. Your cardiovascular system strains, your skeleton compresses, your muscles fatigue faster than normal. Humans could adapt, perhaps, over generations, but comfort would never come naturally there. And the red dwarf star itself flares violently, bathing its planet in radiation regularly. One large stellar flare could strip away atmosphere in hours, sterilize the surface completely. Gliese 667cc is close enough to reach, in theory, but hostile in too many ways. A world that might kill us slowly through crushing gravity, or suddenly through stellar violence. History marked 2014 as the year Kepler 186f became the first Earth-sized planet found in a habitable. The discovery proved that planets like ours existed beyond our solar system without ambiguity. Radius 1.1 times Earth, mass likely similar. Orbiting a red dwarf every 130 days, but red dwarfs emit most energy as infrared, requiring planets to orbit much closer for warmth. At that proximity, tidal locking becomes nearly inevitable over geological timescales of evolution. Same problems return: eternal day facing eternal night, atmospheric chaos in between them. And distance places this historically important world 500 light-years beyond our reach entirely. Even traveling at 10% light speed, a velocity we cannot achieve, journey time exceeds 5,000 years. 50 human generations born, living, and dying aboard the ship before arrival at destination. Can culture survive intact across 5,000 years floating through void with no external contact? Earth civilizations barely last that long when rooted in soil with unlimited resources available. Kepler 186f belongs to history books and scientific papers, not to mission planning documents. A world to admire through telescopes, to study with spectroscopy, never to visit directly. Teagardens Star B was identified in 2019, orbiting one of the coolest red dwarfs known. Just 12.5 light-years away, genuinely close in the context of interstellar distances. Earth Similarity Index calculated at 0.95, among the highest scores assigned to any exoplanet. Mass approximately 1.05 times Earth, suggesting gravity nearly identical to what we experience. The star barely sustains fusion, burning so cool it will outlast our Sun by trillions of years. Any civilization established there would never fear stellar death across any conceivable future. But orbital period of just 4.9 days means the planet circles extremely close to its star. That proximity exposes the planet to intense stellar wind, charged particles streaming relentlessly. Over geological time, stellar wind erodes atmospheric gases unless magnetic fields deflect them. Earth's molten iron core generates the magnetic shield that protects our atmosphere from solar wind. Does Teagardens Star B possess similar protection, or does it slowly bleed atmosphere into space? We cannot measure magnetic fields on planets light years away. We simply do not know yet. Without that protection, even perfect worlds gradually become Mars, atmospheres thinning until nothing remains. Teagardens Star B represents a gamble on one critical property we cannot verify before arrival. Close enough to reach, potentially habitable, but carrying risks that might doom any colony. These 5 worlds demonstrate the patterns that eliminate most exoplanets from realistic consideration. Distance transforms perfect planets into unreachable fantasies beyond any technology we can imagine. Tidal locking creates worlds where only narrow bands remain habitable despite overall potential. Extreme gravity makes comfortable planets into endurance tests our bodies were never designed for. Water worlds offer survival without the resources necessary to build independent civilizations. And stellar violence from red dwarf flares threatens to destroy atmospheres we depend on. Every world discovered teaches us what to avoid in our search for genuine refuge. Now we turn toward the candidates that remain after eliminating the beautiful, impossible dreams. In February 2023, a team of German astronomers published a discovery that had escaped notice for years. Wolf 1069b, a planet orbiting just 31 light-years away, hiding in plain sight among survey data. The planet measures 1.26 Earth masses, close enough to our world that gravity feels familiar. Orbital period, merely 15.6 days, circling its cool red dwarf in a tight but potentially stable. Computer models run after the discovery suggested something encouraging about atmospheric retention. Despite proximity to its star, the planet might hold on to its atmosphere over billions of years. Surface temperature calculations hinted at conditions where liquid water could exist without boiling. What makes Wolf 1069b noteworthy is the absence of obvious deal breakers that doom other candidates. Gravity manageable, distance reachable within generation ship parameters, star relatively calm compared to violent This planet does not inspire poetry or capture headlines with superlatives that excite the public. But in the brutal mathematics of interstellar colonization, boring becomes valuable when everything else kills you. A world that simply exists without trying to kill you is rarer than most people realize. Among the thousands of exoplanets cataloged, that quality alone elevates Wolf 1069b above countless others. Sometimes, the best destination is not the most exciting one, but the one you can actually survive. Ross 128b holds the distinction of being the second closest potentially habitable exoplanet we know. Discovered in 2017, it orbits just 11 light-years away around one of the quietest red dwarfs observed. The star Ross 128 emits fewer flares than almost any other M-dwarf monitored by our telescopes. This matters profoundly because stellar flares represent the primary threat to planets orbiting red dwarfs. Without constant bombardment stripping atmosphere, planets have time to develop stable climates over eons. Mass 1.35 Earth masses suggests comfortable gravity. Orbital period 9.9. Temperature equilibrium models calculate surface temperatures around 21 degrees Celsius if atmosphere exists. That number, if accurate, means Ross 128b could be naturally temperate without any technology. Walk outside without pressure suits. Breathe air if it contains oxygen. Feel warmth on your skin. Of course, the planet is almost certainly tidally locked, like every world orbiting this close. One hemisphere eternally lit, the other forever dark, with all the atmospheric chaos that creates. But if thick atmosphere exists, winds could redistribute heat, creating livable zones across more surface. And Ross 128's calm nature means whatever atmosphere formed initially might still exist today. Stellar wind has not had billions of years of violent flares helping it strip gases away. The combination of proximity and potential habitability makes Ross 128b genuinely interesting. At 11 light-years, traveling at 10% light speed means a journey of 110 years from launch to arrival. Still multi-generational, still requiring technology that does not exist yet anywhere on Earth. But within the boundary where serious engineering discussions can happen instead of pure speculation. We do not need new physics to reach Ross 128b. We need better engineering of what we already understand. That distinction separates realistic targets from fantasies, no matter how perfect they might be. Then, in 2019, astronomers took a closer look at LHS 1140b, a planet located 48 light-years away. This super-Earth has 6.6 times our planet's mass compressed into its volume. Surface gravity would be nearly double Earth's. Uncomfortable, but survivable for human physiology long-term. But new analysis revealed something far more interesting than just another rocky super-Earth candidate. The planet might be entirely covered by a global ocean, though not the crushing abyss of Kepler-62f. Models suggest an eyeball planet configuration, tidally locked with a specific thermal pattern developing. The star-facing hemisphere maintains a vast liquid ocean, warmed by constant stellar radiation without cease. The dark hemisphere freezes solid, ice extending kilometers deep toward the twilight terminator zone. Between these extremes, a ring of temperate ocean circles the planet at the boundary of light and darkness. Neither boiling under constant sun, nor frozen in eternal night, but perfectly balanced in between. If this model is correct, LHS 1140b offers accessible liquid water without crushing pressure. JWST has this world scheduled for intensive atmospheric study during 2025 and 2026 observing. If water vapor, oxygen, perhaps even methane get detected in its atmosphere, everything changes. This becomes one of the highest priority targets for eventual missions within the next century. The combination of relative proximity, potential oceans, and active telescopic study makes it unique. LHS 1140b represents what modern astronomy accomplishes when powerful instruments meet the right target. But 48 light-years translates to 480 years at 10% light speed, spanning 5 or 6. The engineering of ships lasting that long, maintaining life support, preserving culture and purpose. These challenges might prove harder than crossing the distance itself when we finally attempt it. January 2023 brought an announcement from NASA's test team that quietly changed the odds. TOI 700e, a fourth planet discovered in a system already known to contain 3 others. The planet sits just 100 light-years away, far but not impossibly distant by our emerging standards. Measuring 95% of Earth's radius, this is the closest size match to our home discovered anywhere. Orbital period 37 days means receiving roughly the same stellar energy that Mars gets from our Sun. But TOI 700 is a red dwarf, cooler than our Sun, meaning the planet orbits closer to compensate. What makes this system extraordinary is not any single exceptional quality of one planet, but rather the fact that 3 planets orbit in the habitable zone of the same star system. TOI 700d, discovered earlier, sits in the zone, and TOI 700e joins it. If we could reach this system, we would have multiple worlds to choose from instead of one. 3 separate chances to find suitable conditions. 3 different environments potentially evolved. If one planet turns out hostile, 2 others wait in the same system, reachable with the same journey. The probability mathematics of finding perfect conditions somewhere improves dramatically with multiple attempts. And 100 light-years, while vast, falls within generation ship mission profiles considered achievable. At 10% light speed, journey time reaches 1,000 years, spanning 20 to 25 human generations. Difficult beyond anything humanity has ever attempted, but not impossible given sufficient technology. TOI 700e represents a realistic worst-case scenario for interstellar colonization attempts. Far enough to require genuine commitment, close enough that success remains within physical possibility. But everything changes when we examine TRAPPIST-1, announced in 2017 to international astonishment. This is not a single planet offering one chance at finding habitable conditions. This is 7 Earth-sized planets packed around a single ultra-cool dwarf star like pearls on a string. Located 40 light-years away, close enough for detailed study with our most powerful telescopes. 3 of those 7 planets orbit directly through the habitable zone, where liquid water can exist. TRAPPIST-1d on the inner edge, TRAPPIST-1e in the center, TRAPPIST-1f on the outer boundary. The central planet, TRAPPIST-1e, receives the optimal amount of stellar energy for temperate surfaces. Measuring 0.92 Earth radii and 0.62 Earth masses, it offers slightly weaker. Orbital period merely 6.1 days means years pass quickly, though what that means for climate remains unknown. All 7 planets are tidally locked, but thick atmospheres could redistribute heat through powerful winds, carrying warmth from the day side to the night side, creating habitable zones across more surface area. JWST has already begun studying these worlds, searching for water vapor, oxygen, methane in their atmosphere. Initial observations confirm some planets have atmospheres, though composition remains uncertain pending more data. If even one of these 7 worlds possesses breathable atmosphere, it becomes humanity's primary target. And if that one fails, 6 others wait as backup options within the exact same star system. The odds of finding suitable conditions somewhere in TRAPPIST-1 exceed anywhere else we have discovered. This system represents the best balance of accessibility, multiplied chances, and concentrated opportunity. But 40 light-years means 400 years at 10% light speed, a journey spanning 8 to 10 human generations. The ship itself must become a functional society, maintaining knowledge, culture, purpose across that time. Children born aboard will live their entire lives knowing Earth only through stories and recordings. Grandchildren of those children will continue the mission toward a destination none of their ancestors saw. Can human communities remain cohesive across that span without the stability of ground beneath them? Can purpose survive when the goal remains abstract, never approaching, always exactly 400 years away? These questions have no precedent in human history, no tested answers, only optimistic speculation. But if we solve the human challenges, if we build societies that endure in transit, TRAPPIST-1e and its 6 siblings offer the most realistic pathway toward establishing a second Earth. Not guaranteed, not easy, not certain to succeed, but genuinely possible in ways other targets. And genuine possibility, however distant and difficult, is more than most exoplanets can offer us. September 11th, 2023. A date that will mark a turning point in the history of astrobiology. JWST released spectroscopic data from K2-18b, a planet 120 light-years. The findings were extraordinary enough that NASA held a press conference to announce them publicly. Carbon dioxide and methane detected in the atmosphere through precise wavelength analysis of starlight. These molecules alone would be interesting, but what came next changed everything about this world. Dimethyl sulfide, a gas that on Earth is produced almost exclusively by living organisms. Specifically by marine phytoplankton, microscopic life forming the foundation of oceanic food chains. No known geological or atmospheric process generates dimethyl sulfide in measurable concentrations naturally. The detection remains tentative, requiring confirmation through additional observations over coming years. But if confirmed, K2-18b would become the first world beyond our solar system showing evidence of active life. Not fossils, not ancient chemical traces, but living ecosystems producing gases we can measure from here. K2-18b is not a rocky planet like Earth, nor a gas giant like Jupiter, but something entirely new. A Hycean world, named for the combination of hydrogen atmosphere and ocean below it. Mass 8.6 times Earth compressed into a radius 2.6 times larger, creating strong but orbital period 33 days around a red dwarf star, receiving stellar energy similar to what Earth receives. The thick, hydrogen-rich atmosphere extends far above a global ocean, potentially hundreds of kilometers deep. No solid surface exists anywhere beneath those waters. No continents, no islands, no ground at all. Any human presence would require floating structures, artificial platforms, complete technological dependence forever. The hydrogen atmosphere, while potentially breathable with the right equipment, is fundamentally alien to us. Mining becomes impossible without solid crust to excavate. Conventional agriculture cannot exist in ocean alone. If our technology fails catastrophically, no raw materials exist to rebuild from the planet's resources. K2-18b might harbor life right now, making it scientifically invaluable beyond any other discovery. But habitable for alien life does not automatically mean colonizable for human civilization long-term. It is a world to study intensely, to learn from profoundly, perhaps to visit eventually. but not obviously a planet where humanity could establish an independent, self-sustaining society. The difference between hosting life and hosting human life specifically narrows our options considerably. And 120 light-years distance means 1,200 years at 10% light speed. The ship would become a complete civilization before arrival, isolated and self-contained for over a millennium. K218b teaches us that the universe might be filled with life, while still offering few true refuges. We need not just a planet supporting biology, but one supporting our specific biology with our needs. That requirement eliminates worlds that other forms of life might find perfectly comfortable and thriving. Which brings us to August 24th, 2016, the day everything about humanity's future changed direction. Astronomers announced Proxima Centauri b, a planet orbiting the closest star to our Sun. Distance: 4.24 light-years. Closer than any other exoplanet known to exist anywhere. The planet was detected through radial velocity, watching its star wobble under gravitational influence. Mass: approximately 1.27 Earth masses. Radius estimated around 1.1 Earth radii. Orbital period: 11.2 days. Circling its red dwarf star in the habitable zone, despite extreme proximity. The planet is almost certainly tidally locked. One side eternally facing star, other facing eternal dark. Temperature models suggest the star-facing hemisphere could maintain liquid water if atmosphere exists. But Proxima Centauri itself is a violent red dwarf, prone to massive flares that blast radiation. March 2019 brought a stark reminder when the star brightened by a factor of 68 in just 10 seconds. A flare like that, if it struck directly, could strip away any atmosphere in hours of bombardment. Sterilize the surface completely, destroy any life that might exist there, reset everything to barren rock. Whether Proxima b has survived billions of years of such violence depends entirely on magnetic shielding. If a molten iron core generates magnetic fields strong enough, the planet could deflect stellar wind. Earth does this successfully. Venus failed to do this. Mars partially failed, with catastrophic consequences. We cannot measure magnetic fields on planets light years away. We simply do not know yet. Proxima b might be habitable paradise or radiation-blasted wasteland, and we cannot tell from here. But here is what makes Proxima Centauri b fundamentally different from every other world on this list. The distance, 4.24 light-years, translates to roughly 40 trillion kilometers of empty interstellar. With chemical rockets, using technology that currently exists, journey time exceeds 80,000 years. Completely impossible, longer than anatomically modern humans have existed as a species on Earth. But in 2016, something remarkable happened just 4 months after Proxima b was discovered. April 12, 2016. Physicist Stephen Hawking announced the Breakthrough Starshot Initiative publicly, a proposal to send light-sail spacecraft to Alpha Centauri, pushed by powerful ground-based laser arrays. The sails would be just meters across, weighing only grams, carrying miniaturized scientific instruments. Ground-based lasers, powerful enough to accelerate these tiny craft, would push them to 20% light speed. At that velocity, the journey to Proxima Centauri takes just 20 years from launch to arrival. 20 years, not 80,000, not multiple generations, but within a single human lifetime. The person who designs the mission could still be alive when the probe sends its first images back. The physics is understood completely. The engineering is difficult, but not requiring new scientific breakthroughs. Ground-based laser arrays capable of sufficient power already exist in experimental forms today. Material science has developed reflective sails thin enough to be pushed by light pressure effectively. Electronics miniaturization means entire scientific instruments fit onto chips smaller than your fingernail. Breakthrough Starshot represents the first genuinely realistic proposal to reach another star system. Not with humans initially, but with robotic scouts arriving within decades and transmitting data home. If those probes confirm Proxima b has atmosphere, liquid water, stable surface temperatures, next steps: larger missions carrying biological samples, genetic material, equipment to establish presence there. Perhaps embryos with robotic incubators that grow humans on arrival, raised by artificial intelligence. Or suspended animation, if medical science advances enough to make long-term freezing viable. Or generation ships, if we accept the journey spanning multiple lifetimes, but remaining possible. Each approach has technical challenges, but Proxima b is the only exoplanet where these become relevant. Every other world on this list requires breakthroughs in physics we do not currently understand. Faster-than-light travel, wormholes, warp drives, technologies that may violate fundamental physical laws. Proxima b requires only engineering, scaling up what we already know works at smaller scales. That distinction between impossible physics and difficult engineering is the difference that matters. And if Proxima Centauri b proves uninhabitable after we arrive, the system offers other options. Alpha Centauri A and B are Sun-like stars, both potentially hosting planetary systems we have not detected yet. At 4.37 light-years, barely farther than Proxima, they represent backup chances within the same system. One target system, potentially 3 stars, possibly multiple planets within reach of realistic technology. But we must be honest about what reaching even the closest star actually requires from us. Breakthrough Starshot light sails reach 20% light speed, but cannot slow down on arrival at destination. They fly past Proxima Centauri at 60,000 kilometers per second, taking observations for minutes, then to actually land, to deliver humans or equipment, requires ships capable of decelerating at destination. That means carrying fuel for braking, which adds mass, which requires more energy, which requires more fuel. The rocket equation is merciless, exponential, offering diminishing returns with every kilogram added. A ship capable of accelerating to 10% light speed and braking again might mass millions of tons. Launching that from Earth is impossible with any rocket technology that currently exists or is planned. It would need assembly in space, construction in orbit, fueling from asteroid mining operations, an entire industrial infrastructure beyond Earth before the first interstellar ship can even begin. And the journey, even at 10% light speed, takes 42 years one way to reach Proxima. Add time for deceleration, margin for course corrections, realistic travel time approaches 50 years. The people who leave Earth will not be the people who arrive at Proxima Centauri decades later. They will age aboard the ship. Their children will arrive. Perhaps their grandchildren will land. The social engineering of maintaining community across that time rivals the technical challenges. Who governs when no external authority exists? Who resolves conflicts with no appeals possible? How do you preserve purpose when destination remains abstract, never approaching, always years away? Can knowledge survive intact? Can culture adapt without breaking? Can human nature endure isolation? These questions have no tested answers, only speculation and hope about human adaptability persisting. But consider the alternative timeline, the one where we choose Mars instead of Proxima. Mars sits just 225 million kilometers away at closest approach, reachable every 26 months. Journey time with current propulsion technology, 6 to 9 months, comparable to historical ocean voyages. We could land humans on Mars tomorrow if we committed the resources and accepted the risks. No new physics required, no untested technology, just scaling up what Apollo already demonstrated. Terraforming Mars might take 500 years, perhaps 1,000, but it is achievable with known methods. Thickening atmosphere, warming surface, melting subsurface ice, introducing photosynthetic life. Mars will never become Earth, but it could become habitable enough for humans to walk outside. Proxima b might be perfect already, or radiation-blasted hell, and we cannot know without going. The choice is not which world is objectively better, but which is reachable with what we have. Do we terraform the neighboring planet? Difficult but achievable within centuries of focused effort. Or gamble everything on reaching a potentially habitable world decades away across interstellar distances? The answer is, we need both. We need Mars as practice for what comes after. Every technology developed for Mars applies directly to interstellar missions that follow later. Life support, closed ecosystems, radiation shielding, artificial gravity, food production in space. Mars is the testing ground where we learn whether humanity can survive permanently off Earth. And if we succeed there, if we build thriving Martian civilization across the next century, then and only then will we be ready to attempt Proxima Centauri and whatever lies beyond. The search for a second Earth is not about finding one perfect planet waiting for us. It is about becoming the kind of species that can survive anywhere, adapt to anything. Earth will end eventually. Written into stellar evolution, we cannot prevent or delay. But humanity's story does not have to end with Earth if we choose to write the next chapters. We are the first generation to know with certainty that Earth-sized worlds exist among the stars. And we might be the last generation with time to reach them before it becomes too late. The universe has given us 5,000 confirmed worlds, and among them, a handful we could reach. What we do with that knowledge will define us across all the time that follows. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.